Okay, then welcome to this week's lecture. So this week's lecture is about parameter estimation. Before we get into that, like just two small announcements. So last week I talked about homework. We will be giving it next week. So we're skipping more or less this 2-week period, and homework 5 might be the last one and will be out next week. Also, we changed the schedule a bit. So next week we wanted to do what we call it live from the lab, where we take you to the lab and show off how it looks there. We're going to do that in January. Next week will be microscopy, and then in January we'll take you there and show you everything. Yeah, it's here. Yeah. Third floor. We just walk over. You get codes and look at everything. Okay, so this week, so we're going to talk about parameter estimation. Parameter estimation is also part of what we discussed last week, data analysis. Last week, it was more like quote-unquote model-free in some sense. We didn't stick to like the models that we developed in the first part of the course, meaning chemical reaction networks and everything. But we used neural networks. And neural networks are, of course, great, but they can be very kind of black boxy. So you don't know exactly why they're doing things, why they're telling things that they say, that they do tell us. For example, like we had this inhibiting or toxic or not thing, and it was just yes or no. And this week we're going to go into parameter estimation, and this always has like a model attached to it, a mathematical model. And we're going to look at a very simple model that we already looked at, and it's just replication of bacteria. So here, depending on a resource or substrate, so X will be our bacterial species, X plus S gives 2X. And if you remember, we always had this rate constant attached to every single chemical reaction that we put here. Okay. And we want to take this and look at some data, at some time series, and try to find the right parameters that fit the data the best. So kind of in the constraints of our model, we want to know what are the parameters that fit the data the best. And the first question is like, what are those parameters? What do we have actually? So if you just look at this, you might think that there's exactly one parameter, which is the rate constant. This is just some real number. But it's not. Like there are two other like hidden parameters there, which is initial x and initial s. Like if you solve the ordinary differential equation, if you solve the initial value problem, the initial values are part of your parameters. And they determine how the solution looks like, how the trajectory looks like. Okay. So here we have 3 parameters. Maybe let's do that together. So there are 2 differential equations attached to that. One for x, one for s. Just to see whether we remember how this is done. So like dx over dt is in the CRN that only has one reaction. What should I put here? So first of all, does x tend to go up or down in this direction? Well, kind of, yeah. But let's ask a simple question. Do I put a plus or a minus here? Does it go up or a plus? Yeah, because x gives 2x, so there's one x coming in here. So there's plus. And then kind of it's k, the rate constant. And in the mass action, we have the product of these two things, right? X times x. And now we could write something, a second equation for s, which with a minus, of course. In this specific case, it turns out that we don't need to, because like this looks like a 2-dimensional system, but actually it's a 1-dimensional system. It looks like we have x and s, but we only have x in some way or only s. And this can be seen just by noting that the sum s plus x is always the same. In particular, it's equal to the initial sum of these. right? Because we're trading one s for one x. That's all we're doing. So s plus x always stays the same. And if we do that, we can replace this guy here, this s, by something that only depends on x and the initial values, which is just s0 plus x0 minus x at time t. And if we do that here, and we find out that we have a one-dimensional system. This is plus k times x times x0 plus s0 minus x. Okay. It turns out that this you can solve analytically, but we will not use that here. We will not use the analytical solution because what I want to present here should be applicable to any kind of system. And most of the CRNs that we look at, the ODE is not analytically solvable. So just to say that in this case, you can see this as a one-dimensional system, and one-dimensional systems tend to be more analytically solvable than multidimensional ones, but we won't use that a lot here. Okay. So we're taking this mathematical model and the three parameters attached to it, k, x0, s0. That's what we want to know. We will do that with experimental data and also, for a start, with synthetic data. What is synthetic data? So it's where we take the same mathematical model and we simulate it with values that we know. Like we fix some k, we fix some x0, we fix some s0, and then we can just simulate. And then we can see whether we can be clever enough to find these parameters back again. And the second step, we'll apply this to experimental data. And now we go into the code here. Just here, very quick. So here we have like a simulation code, which has this logistic model, logistic right-hand side, and does solves the ODE for us numerically, of course. We do everything here with units. So in all the code, I put like units attached to it. So here, for example, like when we create the synthetic data, we're taking like a true k, and this is like 0.5 and per hour per OD, optical density. X0 has the optical density. S0 has OD equivalence as well. And then with this, kind of we can simulate some data. So this continuous curve is the solution of the ODE. And then kind of to simulate a bit experimental data, first I did two things. First, sampling, just at some points we get the samples. And second, added some Gaussian noise on top of it. It's not really realistic in any strict sense. It's kind of the most realistic thing that you can think of is like a measurements error coming from the measurement device itself. Sometimes they tend to be Gaussian. But like the modeling error is clearly not Gaussian. Okay, so we take these things. So picking the parameters k, x0, s0, simulating them, solving the ODE, and subsampling them, and putting some noise on top of that. As very small point, we use units here. The normal function in Python, solve IVP from SciPy, cannot deal with units, which is why we have written, one of our PhD students has written like a small wrapper around that, which is called solve IVP Pint. Pint is the library that handles units the best in Python. And then you can just give this with units, which is always good to have because people tend to make mistakes with units, including us. Okay, so once we have the curve, then we can think of like finding back our our parameters, and how do we say that we need some measure of goodness, of fit. And this is just the 2 norm of the experimental data. So here, this J of theta. Theta will be the parameters. In our case, it will be K, X0, S0. Will be just the sum of the squares of differences between Y, I will be the time series data that we get. In our case, it's synthetic at first, synthetic plus Gaussian noise. And X, Ti, and theta is the solution of the ODE at time Ti with the parameters theta. And here, of course, the time points that we get the time series is at times Ti and with values Yi. But just the 2 norm is kind of the gold standard optimization loss function for these things. And then we want to find, if we can, like a theta star, which is the arc min, or close to the minimum as we can get of this loss function. Okay, and before we do that, maybe we can plot something which we can call the optimization landscape, which is like how do the values of our loss function depend on the parameters. Of course, we have 3 different parameters. So we're going to make a shortcut. And we're going to make one shortcut, which is like setting capital K to S0 plus X0. So that we have a 2-dimensional system, we only have like small k and capital K. Capital K is kind of the plateau, kind of the where we end, because this will be, once all the substrate is taken up, X will be equal to K. Okay, and yeah, we're just going to plot this here in 2-parameter space with loss function. And for this specific system, that's more or less how it looks like around the true parameters. So here, of course, we have like the different values, like dark is low values, light here, yellowish, will be high values of the loss function. So yellow is not good, dark blue is very good. And here we're doing a log scale of these things, so that's why they can get negative. And here are the true parameters, and we can imagine this like as a valley, right? So like here, we descend kind of sharply into the valley. Here it's kind of elongated, but we see that kind of all the gradients in some sense, they point towards this star here, this optimum. Okay. Bear in mind, this is not completely centered around the star because of the Gaussian noise that we put on top of it. Okay. Right. So this is kind of the best, in the best case, kind of this is what you wish for. You have this single valley and this kind of single minimum, and all the arrows point towards it. So if you're just going downhill, you get there. Sometimes that's not enough. And this is something that sometimes structurally you cannot identify some of the parameters. And let me give like a very simple example at first before we get into kind of our time series here. Let's imagine like an alternative system, let's say of bacteria Y. Like a different species. And let's say we have 2 different reactions for that. Let's say we have a duplication reaction. Let's stay simple without any resources, so just Y gives 2Y, and Y goes to nothing, like a death reaction, a birth and a death reaction. Let's give this rate constant beta for birth, and this rate constant delta for death. Let's write down the ODE for this. So if 1 plus, we have 1 minus. So we have plus beta y. It's a unary reaction, so there's no multiplying two of the species together, and then there's minus delta y. And if we write this a bit differently, then we immediately see that we can never hope for like complete identification, unique identification of beta and delta. Because we can call this difference anything we want, right? Let's call this alpha. And then we see that kind of the behavior of the solutions of this ODE only depend on alpha, only depend on the difference. But you can trade one for the other. You can increase beta and delta at the same time by 2. It stays the same. So this is a case where clearly beta and delta are not identifiable. The difference would be, but them, like the pair beta delta would not be. You can't do it. So this is a kind of a constructed or theoretical example where structurally it's very clear that we can never learn these values beta and delta at the same time. Here we put like an example of something where it's a bit more subtle. And what we're doing here is like we take the same mathematical model that we had here, but we restrict the time series. Let me draw a picture for you. Maybe here. If we have a time series like this, like t, and here we have x, like a complete time series would look like something like this. So we start, and then at some point we level off because the substrate runs out, the resources run out. And more or less for this specific system, one strategy to do this, all of this, is kind of to identify first the capital K, so the sum of x0 and s0, which is kind of the final value of the plateau here. Then the second step, we can kind of look at the initial growth rate here, and the initial growth rate will just be k, small k times x times capital K, more or less, if k minus x is small, if x is small with respect to k, which most of them is, and then kind of you can look at one of the derivatives here, and then you get k. So it can be like a two-step process, but the first step here would be to identify the plateau. Once you have that, then you know what to divide by here to get the k. Again, you have to divide by capital K and by x0 at the start. And of course, x0 you can just identify by looking at the first value here. But now what we're doing is kind of we will cut the time series and only look at the first part. And if you do that, it will be kind of clear that you will not be able to identify capital K. You don't know how far it will go. But you can identify something else. You cannot identify exactly the rate constant K, but you can identify something close to it. So let's again write this just with a small simplification. So let's say initially for small times, we'll have that this ODE will be more or less k. This is of course exact k times x. And then at the start, if the plateau is much higher than the initial value x0, this will be more or less only k, like capital K, the plateau. Okay? And we will never be able to exactly figure out capital K, but we can figure out the product of small k times capital K. So just to write this a bit differently, small k times capital K times x. And this product we can just find out just by looking at the derivatives at the start. Because of course the solution to this like an approximate solution of course will be x0 times e power k, and t. And we can just give this another name. Let's just call this mu, which is the initial growth rate of this thing. And this we can totally find out just by looking at the start. We know like how exponentially this, with which exponential rate this will go up. So that means for us that we will not be able actually to identify small k. We can't do it because we can't identify capital K, but we can identify the product. So once we change our parameterization, we are able to figure some things out. So in particular, here now if we're changing, I didn't put it here yet, but if we're, if once we're changing here, the mu to small k times capital K, then mu we can identify, even though we cannot identify capital K. It's the same thing that we just had before, where we can identify the difference, but not the individual things. And here now, like in our original parameterization, we could not figure out capital K or small k, either one of them, but we can completely identify, even at the start, in that exponential phase, small k times capital K. And let's call that mu. Okay, so sometimes you have to kind of rethink a bit what you're doing. And here, this is just like again, the landscapes of the full growth curve with the true value here, and the exponential phase only growth curves, where we only look at we give it as time series only the start. And here we see, and here we have this is again small k versus capital K. And here we have the true value. And we see kind of that in these directions we have like a valley. Like here it's higher than here. Like this is lighter than the dark blue tones here. But we see also that along these lines we have the exact same values. So even if here is the optimum, if this is fine, then this is fine also, then this is also minimum, this is also minimum, this is also minimum, and so on. Which kind of shows you that here you have many, not only local minima, but like global minima. You have like a whole continuum of these. Okay. Right, and so if we're changing our mindset, then here we can identify at least the initial growth rate, mu, even though, of course, we cannot know the carrying capacity, capital K, if we only look at the exponential phase. Okay, and then we come to the question of, like, how do we, let's say our system is well behaved in the sense that maybe there is a unique minimum or close to it. How do we algorithmically find these things? And more or less there are two answers. And the first one, I'm sure you heard of, like just gradient descent. Gradient descent is mostly what kind of neural network relies on. Like the optimization algorithms of neural networks are mostly a variant of gradient descent, with some randomization and some inertia effects, but more or less that's it. And gradient descent, of course, is a very local kind of way of looking at things. So you would have like don't know, you point here and you have some your contours here, and here let's say here it goes down, and then let's say here it goes down and here up, and then your gradient would point towards the direction of largest increase, and then you go in the other direction if you want to descend the gradient. So kind of the most basic like equation for that is like your update of xk plus 1 in the k plus first step, just to take xk and then subtract some alpha, some rate alpha times the gradient of your loss function j. So I'm sure you have seen this. What is mostly used in kind of the standard Python libraries, at least, is a variant of gradient descent also. That's kind of neat, which is called this LBFGSB. Lots of letters. The last one stands for bounds. I'm not exactly sure. Like the others are some names. And what they do is kind of they take into account not only the gradient, which is of course the first derivative, but also the second derivative. It's called the Hessian matrix. And just to motivate that a bit, just to give you an idea of why the second derivative will come into play here, let's do a small intuition of why this makes sense. And then of course, there's a second component to this algorithm, this LBFGSB, which is that they don't like analytically or exactly identify the Hessian HK, but they do it, like they approximate it step by step. But we won't go into that, how that is done. But just let's do like an intuition why the second derivative will come into play here. And of course, what we can do is like we take our loss function j and we do like a second degree Taylor approximation, which is of course the constant term, which is just around xk. Let's say xk is our current value, and we want to know how we should update that to find the minimum, which is just j of hk, and then plus, and then here is the first derivative. Xk, just the transpose of that times x minus xk. It's the linear term. And then there's let's do the second term as well. So the term, the quadratic term as well, which is x minus x0, xk, x minus xk. Here transpose, here not, and in the middle we have the Hessian matrix of xk, which here is called hk. Okay, once we have that, the question is like, how does this approximation help us identify the direction, the next update that we should take to minimize j of x, excuse me. And this you would just do like you would normally do, like real analysis, minimizing a function. This is multidimensional, but it doesn't change it a lot. So we would just get the derivative of this whole thing and set it to 0. Now derivative with respect to x. We treat now xk as a constant. So we want to set 0 equal to derivative of j of x here. And then this is more or less, this is a constant term, disappears. This is a linear term, so you only retrieve the coefficient here. And then here is a quadratic term. Sorry, I forgot something. This is 1/2 to get the Taylor series. So here you have a square, more or less like in one dimension. What you do is like kind of the 2, like you remove the 2 from the exponent, put it here, and the linear term remains. This is plus hk times x minus xk. And the minimum of this function should be your new like xk plus 1. So this is the xk plus 1, like a new value that you take and hope that this is the minimum. One, of course, here we didn't check whether it's the minimum or the maximum, but just to get the intuition. And of course, if we do that, so let's say we put all this to 0, then we get like xk plus 1 minus xk, just this. And if hk is invertible, then we can put like this equal to nabla, so gradient of j of xk. We multiply by the inverse of hk from the left, so this is hk minus 1. Then we're just putting this on the other side. And looking, I guess I made a minus. Yeah, sorry. First this was minus here, and then we're doing the plus here, so this has to be a minus, because we're putting the j of xk to the other side. So this should be a minus here. Okay? And then you get, like, now using like a second order Taylor approximation, you get this a bit more sophisticated formula for your next update, which takes into account the Hessian, so the second derivative, and more or less what it takes into account is kind of the landscape, the curvature of the landscape that we have. Kind of, if it's elongated, kind of it takes into account that it is elongated. Of course, there are some algorithmic tricks that are not going to go into detail here. We didn't even go into detail here in the text. It's much more involved than that, but there is like an iterative approximation that you can do to approximate the Hessian. Okay, the good thing is that all of this is already implemented in SciPy. So just you take SciPy minimize, we took that kind of, we imported that at the beginning, and here you can just say the method should be LBFGSB. And you can put these bounds. This is what this dash b means. Is kind of it will respect your bounds if you want that. And yeah, and this is we just do like this clever form of gradient descent, but it's still like a totally local kind of algorithm. And here with some initial guesses. So here we took initial guesses that are close, just to show off the algorithm, that are close to the true values, just to see whether it can find the values in an easy case. It turns out that yes. So here we have the true values, and here are the values that kind of our gradient descent found, and they're kind of close. Right? So here, 0.49 and 0.5 is a true one, and the other is also close. And here's also kind of the simulation curve coming from these parameters is very close to the data. But this, of course, was kind of like an easy case. Local methods can go wrong, and this is what we show in this next kind of short snippet here. Here we will do n trials. So n times we start the whole optimization algorithm again. And now we take different initial values for mu, k, and x0. And here we just take them uniformly between some bounds. And then we're running these 10, and we're checking whether, this we do here, whether we come into 10% of the true value, whether the relative error is bigger or smaller than 10%. And this is what we call the success rate here. And we're doing 10 trials, and we fail 7 out of 10. Just because they're too far away, that they don't find their way through this landscape. Okay? And this means like, so for some of them, of course, it finds it back very well, but here it's kind of very off, like the true value is 0.5, and here it says 1.4, which is, of course, way off. they are exactly the same. It's not on the seed that this depends on. I think this is by chance because we're picking the different initial values. So it's not clear that these will come out to the same value. There's more chance than. You're starting your algorithm but with different initial values. So it's not clear that they come. Here they're the same. But I don't think that there's a pattern behind this. No, this is not the same test. No. These are the final values. Yes, they're not the initial values. Yeah, good point, yeah. Now, we took 10 different values, not all on the same seed. So the seed is evolving, so we have this RNG object that we're using here. This RNG init, which we only use for this. We have also another RNG that we use for the algorithms. To separate them, we put like a new RNG object just for this, and we use them in sequence. Okay, so this just means gradient descent, awesome if you're close, can be not awesome if you're far away. And this is where global optimization comes into the picture. Global optimization, more or less what it does, it is of course also like tends to iteratively go to better and better values. But here, for example, the one that we took, differential evolution, and also others like particle swarm optimization, what they have is they don't have like one point that they're following, but they tend to have like a population of values that they're following. So they're exploring one area of the optimization landscape and another one, and another one, and another one at the same time. So kind of they have a higher chance of chancing upon good values. Differential evolution here, it's one of the standard algorithms. It tends to perform well on time series we found, on these types of time series at least. And there's some updates, so you have a population of values, and what you do is like you take like a triple of them, A, B, and C, and you do a mutant of picking like a base value A, and then the difference of B and C with some rate attached to that. And then you get like a new mutant vector, and this mutant vector you don't immediately put back into the population, but you first, like you keep a random subset of the coefficients in the vector of them. So maybe the first dimension you keep from A, and then the second dimension you keep from A plus F times B minus C, and the third one maybe you keep from A again, and so on. And this gives you like enough of randomization that you can hope that you get, that they explore kind of a lot. And once you do all that, then you check whether your final value that you get here, the J of trial, is smaller than, let's say, J of A. If it is, then you replace A by trial, by this new vector, and you go on. So you have kind of this evolution thing where you combine two vectors, and it's differential because you're going in one direction. That's a differential of two, the difference of B and C. Okay, so this is how the intuition works. Again, this is something that has been implemented in SciPy, so we can just take that. Again, we imported that a bit up. And here we don't actually need initial guesses because there's a population of them, but we do need to provide some bounds for each of the parameters. And if we run that, so here, maybe we can run, or maybe actually I would like to run both live. So again, so let's go back to gradient descent, just to show you how kind of the time complexity of these things. So this was kind of quick. It took 0.46 seconds, and starting from a good initial guess, found its way. These are the 10 trials. It takes, of course, longer because now it's 10 of them, but it's around like 10 times what we had before. Here we get now, of course, the same success rate because we have the same seed. Differential evolution here, because it's a whole population and you need to evaluate the loss function more often. This is quite a bit slower. Not horrible if I remember correctly, but around like 20 seconds or something. Oh, no, not too bad, actually. Around 10 seconds, which is kind of times 10 or 20 the time of one gradient descent run. And here we see, just for fun, we plotted like how often the population here, the evolution of this population, had to evaluate the loss function. And here was 1,900 times. And so this is, of course, where the slowdown comes down to, because evaluating the loss function can take some time. And which leads us to kind of this observation that you can have both of the best of both worlds in some sense, which is, and this is a pattern that you can try a lot when you do optimization problems. You can try first global, then local. Run some global scheme. Here is differential evolution, but you can pick another. And once you identified like a good candidate, then minimize it just by gradient descent. You fine tune to find the kind of the best thing that you can do. And here, what we do is actually we do like first a quick global search. I think we had 300 iterations of differential evolution in the first version. Here now we only take 20, so much less. And then on this quick differential evolution result, then we put our gradient descent algorithm. And this is the result. Takes longer than gradient descent on its own. But here it kind of found a very good set of parameters, but not in like the 10 seconds or whatever that we had with only differential evolution, but here in 5 seconds, which is faster than only differential evolution. But we didn't need to have like a good guess. We only put the bounds. So kind of it found the good initial guess via differential evolution, and then it kind of fine-tuned with gradient descent. Okay. So, and we take this scheme that we now learned, global, then local, to experimental data. So here, we put into the lecture notes kind of plate-reader.txt, which is kind of just OD measurements over time that we took in our lab on the third floor here, just of standard growth curves. We put we put our E. coli, or like I think 8 colonies in parallel, and we just let them be measured every, I don't know, 10 or 5 minutes in the plate reader automatically, and then we get the OD readings. So here's just some code to ingest the data. And oh yeah, we have wells from A to H. One of them is the control, so which is empty, so we have 7 growth curves actually. Okay. Yeah, and it's over 26 hours. Every 5 minutes, that's more or less comes down to 213 time points. And this is just a graph of all these things. We have 7 of the curves here. We have one of the curves, which is the blank with the control, so there's no bacteria in it, just to calibrate. Here at 0, of course. It has to be 0 because that's what we define it to be. We subtract A1 from everything. And here we have the growth curves. And let's just pick one of them and try to parameterize. Well, know how to do that. So we do, again, our scheme. We do differential evolution, then minimize. Minimize. Of course, minimize the function minimize, which is gradient descent. And then we see what it tells us. Of course, it finds some values, which is good. And it doesn't sound completely crazy, like a plateau of around 1 OD, which isn't crazy. Like an initial value of 0.1 OD doesn't sound crazy. A mu, so initial growth rate around 0.3 per hour, which is absolutely not crazy. Like this maybe around 20, 30 minutes. To guess whether it doesn't sound crazy, but let's see whether it looks crazy. So this is a fit of our data versus the experimental data. This is the simulation based on our fit and this experimental data. So we see that kind of it has some good things going for it. We kind of finish at the same plateau here. We roughly going here, like there's a different behavior at the start. Kind of here, more or less what it looks like is we go up with one rate, and then here with a second rate, and then we go into the stationary phase. That cannot really do that with with our model that only has one substrate. Here is just like the difference of both of them, of course, telling us that at the start we have like a huge difference or a larger difference than at the end. So we could already be happy with that. So kind of it's not crazy to say, okay, our like first order model, which is kind of this x plus s gives 2x, is kind of well parameterized, and of course it depends on our use case whether that's good enough for us. Just at the very end, I want to go into like, because we had these two different rates, I want to go into like changing the model. And sometimes you do that. Like you look at the data and you're not happy with what you see. I would argue that here we can be happy for most cases, but if you really want to fit your data better here, because we see that we have like a higher growth rate and then a slower growth rate, it's not crazy to think that you might have two different substrates, two different resources. The first one that is taken up, that is used at the beginning, which is faster, and the second one, which is slower, but then takes over in the second step. And the nice thing about like this parameter fitting pipeline that we have now is that we can just try and see what we learn from this, if we can learn anything from parameter fitting this model. Okay, so here we just input the two resource model, of course with units here, and then we give this to our solver, and here are the two models. So first of all, like mu underscore s is the first model, a single model, and here are the same that we had before, I think, or very close to it, 0.249. I think it's more or less we had. Ks was around 1. And here now we have the parameters of the second model. And we see already one thing, or two things actually. So first there's a K1 and a K2, the point where the first resource runs out, and the point where the second resource runs out. The first resource runs out at around 0.24. So kind of in the early stages. It could fit with what we've seen kind of when it went from very fast to only kind of fast. And K2 hits kind of the 0.9 ceiling of our plateau, which is also makes sense. Also, the first one is quicker than the second one. So the duplication rate for the first resource is much higher than the second rate, at a factor of, I don't know what it is, factor 5 or something. Okay. This already tells us that maybe our intuition of like one fast resource and one slow resource might be true. Of course, we can kind of, it's just looking at curves, but so here we have everything. We have the data in light blue with a single resource that we had before in red, continuous red. And then in dark, continuous blue, we have the two resource model. And kind of we might have two things that we like about this model. So first of all, like the best fit for a single resource didn't actually start very close to the initial OD reading. So kind of it was kind of, we could fit the curve, but we had to reinterpret the first OD reading, which is kind of weird. With the two resource model, we can stick kind of, at least for this curve fit, much closer to the initial OD. And then we can kind of follow like the first phase to around 0.24 or whatever it was, and then it goes to the slower phase. And we didn't have to do a lot for that. Kind of we thought about this model change. It was kind of quick to put in. So here actually we put it into ODEs. With the CRN modeling with MobSpy, it might have been even quicker than that actually. And yeah, and here kind of there is some biological interpretation of this, which then can be investigated. Now we could go into kind of figuring out what is the first resource, what can be the second resource. Okay. Yeah, that's it. Just a small point, yeah, about these growth curves. They often tend to look like this, actually, bacterial growth curves. Often they do have like depending on the medium, but in LB medium they do tend to have like a diauxic shift here, or diauxic-like shift. And this can be found by, or can be supported by parameter fitting of these two models. That's it. Just a small recap. So this week we did parameter fitting, meaning we start out from a mathematical model, which are raised here, but we have a model and we have time series data. Of course, the more interesting time series data is from experimental data, from experiments. We did synthetic first, but of course the meat was in the experimental data. And then we try to find the parameters of the mathematical model to fit the time series. And if our model is good, then this interpretation often has really rich information. For example, in the two growth curve model, like even a single resource model has some nice information. But here it was kind of really this first growth rate, second growth rate. We just had that by mathematical optimization. We found that and we could try to interpret this. Good strategies are global, then local. It's a very general optimization technique. Very well supported with tools, of course. You can take like just off-the-shelf algorithms from SciPy often. Sometimes it's not as easy, but in our case here we could. Yeah, another thing was sometimes parameters are not identifiable. So sometimes you have the choice between multiple parameter values. In our case, we found, like with one example where like the parameters were not identifiable, but the difference was, or kind of the parameters were not, but the product was. And sometimes that happens, and then you have to adapt, and you have to kind of concede that you will not be able to know these unknowable numbers. That's it. In the problem session, you will again look at kind of synthetic data and experimental data, and try to find the parameters and try to compare different strategies and different noise levels on these. Do you guys have any questions? Yeah. It's not as clear. So analytical results are kind of rare in this domain. You can prove some things. So first of all, the analytical results are rare. In practice, it tends to work very well. You can, of course, prove some things. So you can prove that kind of this rule, and in particular, sometimes you have variance where you inject some randomness, like some real randomness on top of that, on top of this rule. And then you can prove that kind of with probability 1, you explore kind of sufficiently the whole parameter space. And then, of course, you will find the minimum if it's there. And if close to it, if it's well behaved, if it has a valley. Yeah, in general, at least I'm not aware of too many analytical things that tell you, for example, that in this case, for this CRN, you will find these nice values. So, yeah, there are analytic results, but they tend to be kind of artificial in some sense. Also a parameter. It's not clear which one to choose. You can also try one. Yeah, and kind of I would say also, like just underlining what you just said, like I would say like once we are in this small value, like small difference area, gradient descent is much better than that. You can also do that. Yeah, definitely. Yeah, that's a very good point. Yeah. Okay, any other comments, questions? Okay, awesome then. Thank you, and have fun with the problems.